Hey, I'm just making another quick update video about some of the things I've been working on, which, it's been a pretty busy semester, and I've signed up to do a bunch of stuff. One thing that someone asked about in a previous comment on the first entry was what if I could talk about Schwartzian derivatives, and unfortunately, I don't really know much beyond the Wikipedia page, but that person also asked if I could explain my name, which, yeah, so it's a Latvian name. It's basically the analog of like Christopher over there, which means follower of Christ, which is not true by any stretch of the imagination. But it's, I just think it's a really cool name nonetheless. And my last name is Balladis, which translates into pigeon. So one nickname for myself is Christ Pigeon. But what have I been up to in terms of mathematics? Well, of course, I've been working on my thesis. Behind me here, you can see I'm doing some stuff to do with connections on vector bundles, more specifically super vector bundles. And here's some, things, you build things that represent cohomology classes out of it. And so here's some application of the Poincare lemma to those classes. Some other neat stuff I've been doing, though, I'm going to be making a video for the Kangaroo Math Contest. It's a contest for grade school children across Canada. I also signed up to participate in something called the Prison Math Project, which I'm really excited about. It helps connect people who are inmates and wanting to learn mathematics with mathematical pen pals, basically. And so that's all getting underway. I'm really excited to start doing that. And, and then, of course, lean. So someone asked me if I could explain more about what lean is and what it does. So in a moment I'll show you some stuff on the computer, but basically the idea behind lean is that humans make mistakes. We trust a computer to factor large numbers better than we trust a human, even the brightest human with a pencil and a piece of paper. So the idea is, well, why not trust computers with our logic as well? And so the hope is that the idea is that basically all of formal mathematics could be formalized in the language of a proof assistant, the popular ones right now being Coq and Lean. And a lot of progress has been made towards this. One of the big famous first milestones that people programming Coq made was they programmed the Fate-Thompson theorem into that language and formally verified it. More recently, Kevin Buzzard has been leading this project to teach Lean to undergraduates and to graduate students as well. And right now the goal is to get all of undergraduate mathematics formalized, which they've made quite a bit of headway towards that goal already. And then from there, it's the rest of mathematics. Let's get it all verified formally. Okay, so as an example, you can see here's some lean files I've been working on. So this is what lean looks like. So over here in sort of the main part, here's a proposition. So this is a theorem we want to prove in formal logic. And you can see from the symbols here, this is just formal propositional logic, right? So I'm proving the statement P or Q implies R, if and only if P implies R and Q implies R. And so all of this junk, so the green stuff is comments, but this may look like total nonsense if you're uninitiated, just as Python code would look like nonsense to someone who hasn't programmed that yet. But this is how the computer formally verifies how this is true. So as I click on different parts in the proof, if you look over to the right hand side of the screen, it keeps track where you see the sideways T here, it keeps track of what the goal is. And so you can see as I click further and further down, things split open. I get different goals, and the things that are in yellow are the different assumptions that I have. So as you can see, as I click down the proof, the goals change, my assumptions change, and it slowly moves towards the end until I've finally demonstrated the result. So that's lots of fun. Okay, so I realize that's kind of a heady sort of look, but I'll just show you some examples of some lean files I've been looking at. For example, I was following Kevin Buzzard's video. Here's the definition of a group formally in lean. So you can see here we have the group axioms. There's associativity of multiplication, the fact that we have an identity, the fact that we have left inverses, and then you can go on to prove things that like right inverses are the same as left inverses. Here's some topology built up in lean. First, if I scroll up, here's the definition of the limit. Again, so if you look at these symbols, you should recognize most of this from second year calculus or intro analysis, for all epsilon and the real numbers. So the real numbers are programmed into lean already, with epsilon greater than 0, the rest of the definition limit. The only part that looks different is maybe just writing abs instead of, the normal absolute value bars. And, here's the proof of some basic theorems, right? The limit of the constant sequence is just that constant. The sum of the limit is the limit of the sum. And then we get on to other things here, like here's the definition of a topological space. So again, there's all this blah, 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 fancy extra stuff going on. This is maybe not as transparent to see, what we mean by open sets. But again, we still, we have an axiom here telling us that the union, arbitrary unions of, or finite intersections of open sets are open, arbitrary unions of open sets are open, so on and so forth. So if you're interested in learning lean, which I think you should be, because I really feel like this should be the future of mathematics, and will be if there's any sense in the world, is go to the natural number game, which Kevin Buzzard created. And so this is a fun little game. It's sort of set up like there's dungeons and bosses, and you go through and you learn how to prove stuff in lean. So, as a very basic example, we prove that for all natural numbers, x times y plus z is x times y plus z. Okay, not a very exciting theorem necessarily, but we got to start with the basics somewhere, right? So it just shows, there's basic tactics to prove these equalities. And then as we move on, there's more complicated things going on. So anyone who's done some formal logic or set theory knows that proving things like commutativity of addition or multiplication takes a bit of work. So for instance, over here in multiplication world, if we go to the so-called boss level, let's find, there's a number of steps here, but they're all built up from these different theorem statements that you beat in other worlds. So this is a great place, even for beginners, to get started in lean. And yeah, I guess I'll basically do it for this video. Hopefully I'll be uploading some interviews soon. So speaking of interviews, if you know any mathematicians, if you are a mathematician, if you're a student, or you have a professor that you think would make for a good interview on my channel, please let me know, or better yet, tell them. You can probably find my my Gmail through my YouTube account. Tell them to email me through there and get in touch with me, because I'm looking for people to have on. And in particular, the last couple of weeks, there's been a lot of stuff on math Twitter about just like a stupid amount of racism and transphobia in mathematics. So in particular, I think we need more representation and voices coming from those communities. So like what I just said, doubly so if you know someone who belongs to one of those communities, because I think it's really important right now to be getting those voices out there as well. So yeah, stay tuned.